Hola, ¿qué tal? Muy buenas tardes. Bienvenidos a esta primera conferencia de la Escuela de Invierno de Inteligencia Artificial del Consorcio de IA de Conacyt. Les pido una disculpa por el retraso. Vamos a estar grabando esta conferencia para poder transmitir después los contenidos con los 8 centros que conforman esta alianza estratégica. Les comento que uno de los grandes objetivos del Consorcio en Inteligencia Artificial es precisamente la difusión y el conocimiento de todo el trabajo que se está haciendo en conjunto entre los 8 centros de investigación y también para comenzar a difundir, dar a conocer más todo lo que tiene que ver relacionado con la temática de inteligencia artificial. Así que es por eso que este esfuerzo que estamos haciendo el día de hoy por poder compartir con los 8 centros esta conferencia se va a estar replicando de tal forma que se forme una comunidad interesante de comunicación en temas de inteligencia artificial. Los invito a que continúen al pendiente de nuestras redes sociales, de nuestro sitio web, porque seguramente ahí podrán estar encontrando todos los contenidos relacionados a las temáticas que seguramente les van a interesar mucho. Ahora bien, para continuar ya con el programa y no seguirnos retrasando, le cedo la palabra a la doctora Silvia Fernández, que es la gerente del consorcio, que nos va a hacer la presentación de nuestro ponente de esta tarde.
Yo como estoy muy alta lo hago desde aquí abajo. Bueno, yo les voy a presentar a nuestro conferencista de hoy. Él es Jon Seaton. You're welcome, Jon. Jon es un experto en ciencia de datos con un triple grado en matemáticas, física e ingeniería de la Universidad de Wisconsin. Ha trabajado como investigador en el Media Lab del MIT y ha colaborado con Apple, Pandora Radio, Cisco y Hyundai, dirigiendo proyectos de Big Data e inteligencia artificial a gran escala. La experiencia de Jon en aprendizaje automático e inteligencia artificial abarca una amplia gama de aplicaciones industriales, desde la reconstrucción de imágenes médicas hasta las finanzas. Actualmente, Jon es director de ciencia de datos en Functionize, dirigiendo el desarrollo en aprendizaje automático. Jon describe a esta empresa como un equipo de desarrolladores apasionados centrados en la construcción de la solución de pruebas de software más inteligente del mundo. Es una empresa de rápido crecimiento con sede en San Francisco, California, y con colaboradores en todo el mundo que ofrecen la primera plataforma de prueba de software de inteligencia artificial basada en la nube. Pues nada más vamos ya a cederle la palabra a Jon y esperamos que disfruten y aprovechen esta conferencia. Muchas gracias, Jon, por estar aquí.
Hola. I'm going to be giving my presentation in English, so that's all for Spanish for today for me. So welcome. My name is Jon. I come here, this is my first time here visiting. I come from San Francisco, California, also known as Silicon Valley. A lot of big tech companies there, and I work in the tech space. Currently working on a company called Functionize. And what we do is we use artificial intelligence to test software and apps and other applications. So just a little overview of my talk today. So I'll give you a little overview of the company itself. Then we'll go into some detail on some of the techniques that we use. Okay, so these are some examples. We use supervised learning, unsupervised learning, reinforcement learning. Okay. Then I'll also talk a little bit about another technique we use called boosting. Can be very useful. And then we'll go through some other examples as well. I'm going to try not to be too academic here. I want to sort of explain how we use these in the industry in practice, okay? Because I think other modules in the conference will go into more detail on the mathematics, okay? So I want to sort of explain more how we use this and apply to in the industry. So here's a little background of the company. So we started the company in 2013. We did a lot of development work. Our first co-development effort we did was with Salesforce. I'm sure many of you may have heard of them. That was one of our first customers. We had our first paying customer in 2017. Also in 2017, we began working with Google on some projects with regards to anomaly detection. And basically in the release process of software. Then we also started working with Mar Labs, earlier last year, 2018, and we've also began working with Hyundai Motor Company, testing the software in the cars. It's a very, very interesting problem. So basically, the display, if you are familiar, there's an LCD display in the car. It's basically an app, right? It's basically an app, and we can go through and we can test that application. So overview of some of the companies we work with: Salesforce, Hyundai, Google, TurboTax, Zenefits, and a number of companies. So we've grown the company quite big. Today, we're about 50 people now. We've grown to about 50 people. We have some people in San Francisco. We also have some people in India, and we also have some people here as well. Julio, you guys know Julio, right? Has been helping me with this project. So this is some of the companies that we work with. So why do companies want to work with us? So basically, the idea here is right now, in the software industry, software keeps growing, right? So there's always more code being written, and the problem is that how do you go and test and verify that type of code, okay? So today, what people do is they hire what's called QA engineers, and these QA engineers go through and they manually test these applications, right? They click on buttons, make sure these applications work, right? And because the software is so complex, you end up hiring so many QA engineers, you have almost as many testers as you have developers, okay? And so one of the objectives for our company is to use artificial intelligence so you can scale that testing without having to hire all of these QA engineers. And as a result, this ends up saving a lot of money, right? Because the artificial intelligence can do this process more efficiently. So some examples, we can save companies over $500,000 per year, which is quite significant savings, right? And also the time that it takes to deploy the software, because you don't have to go and manually test it anymore. We can do this automatically, right? So instead of taking days to deploy a new system, we can deploy your software within hours. So it's very, very useful, right? Also, there are examples where you have mission-critical applications, for example, think in like the medical space, right, where it's like the software must work and it must be correct, right? So it's difficult to find solutions for that. And you also have cases where these software applications have 30 million lines of code, right? 30 million lines of code. You can imagine it's quite big. So how can you test a software that's that big, right? And so really the only way is to use this type of artificial intelligence, right? And then also for IoT space, right? Another area that we're focusing on, right? To get better user experience for IoT applications and also improve productivity and cost savings. So sort of the trade-offs in the software industry. So you have developers and innovation on one side, right? But you have quality and user experience on the other, right? So it's how do you balance the two, right? How do you maintain high-quality products, but also be innovative, right? And it's difficult, right? Because if you only have so many engineers that are working for you on your software, they can either do one or the other, right? So how can you do both? Well, to do both, you can use our product, for example, Functionize, to basically reduce the need for doing that QA and basically automate it. So it improves this trade-off. And so this is basically what we consider today. This is how it works today in Silicon Valley, okay? You have developers and QA engineers. They're about proportional, right? About the same. So the idea is can we use artificial intelligence to reduce the number of QA, but maintain your developer team, right? So this is sort of our objective as a business. So let's talk about a little bit of our data platform. Okay, so we collect data from three main sources. First is the client, the user. Okay, so this is the customer. We'll go into our website and enter in data, enter in test information. Okay, we also have modelers. The modelers go through, they can go and model applications. For example, they label data in an application, right? So for example, you might want to label a button or an input box, right? And then we also have some crowdsource elements as well. So we can crowdsource some of the labeling. So those are the three main sources of data that we push into the platform, right? So then we push all of this data. So this is the big data project, right? So we push all of this data into the platform. We generate models, right? AI models, machine learning models. We then use those to test applications in the cloud, okay? So we use Google Cloud. So we can basically run your application in a virtual environment, right, in the cloud. So for example, we can run 10,000 tests all at the same time on your application, right? So it's massively parallel. And then at the end, we then show you the results of those tests. So this is a basic overview of what our business infrastructure looks like. Okay, so then here are the main points for how do we improve this testing. So the idea is to make the testing simple, right? So in some ways we make testing simple, right? We have a way to have the modeler create tests. We do natural language processing. So for example, you can go into our platform and type, I would like to test the login functionality, right? And we can build an actual test to make sure that the login is working, right? All with natural language. It's very cool. Then we can also have a way to do autonomous test creation. So basically we have a scraper or a crawler that can go through and crawl your application automatically and test for different types of anomalies. So oftentimes, a developer, maybe they make a mistake when they release their application. Maybe there's a button in the wrong place, right? Maybe it's misaligned. We can actually test that with computer vision and verify that the application is working correctly. Another issue is durability. So how do you build tests that are durable, that always will work, right? So you can imagine, as developers are constantly developing, right, code, the applications are changing, right? How do you actually test applications that are changing all the time, right? And so for this, we use reinforcement learning models to do that, okay? We also use visual template recognition and meta modeling. The third point, efficiency. So once you've built these tests and we run the tests and we say, oh, well, you have certain failures in your application, what do you do, right? So one thing we've been able to do is we built a root cause analysis system. So you can go through and if a test breaks, we can actually tell you why did it break. Oh, well, it broke because this line of code over here is incorrect, all right? So we were able to build models to figure out where the applications are breaking. It's not always obvious. Right? It might be something that is many steps back that caused a break in the future. Right? So there's a lot of dependencies. We also do temporal anomaly detection, right? So if you think of a time series, and maybe you have users visiting a site, and all of a sudden the user rate drops off, right? That would be a type of anomaly. Maybe something is broken, right? So we do anomaly detection over time series. We also do anomaly detection visually with computer vision. And then finally, scalability. Like I said before, you want to be able to scale these tests, right? So we use the cloud, obviously, to do that. And it also improves coverage, right? So like I said, you have applications that have millions of lines of code, and not one person can go and test that. But using AI and the cloud, you can go and test every piece of that application very easily. Okay, so that's a basic overview of our company, what we're doing right now. Does anyone have any questions about the company itself? Okay, so now I'm going to start going into more about machine learning and what we do with it. So I just wanted to start with some definitions. So what is machine learning? Okay, yes? It doesn't automatically correct it. It identifies where it is, right? But it doesn't automatically correct it because we don't necessarily know the intent of the application, right? So that's difficult to know, right? Because if you did, you could just build a whole application, right? You can imagine you can actually build an algorithm that writes code, right? Write code to write code, right? But because you don't know the intent, you don't know what's the purpose, right? It's difficult to fix automatically. Maybe some things you could, but in general, I say would be very hard, right? Yeah. Yes. Mm-hmm. 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 Yeah. Mm-hmm. Mm-hmm. Yeah. Yeah. No, I'm going to go into some different techniques and things that we've done. Yeah. So, but let's start here. Let's start at the beginning, okay? So what is machine learning? So my definition, and everyone sort of has their own definition, but I think of machine learning as a set of techniques used to achieve artificial intelligence, okay? So there are many different, you can actually create intelligence in software like manually, right? Every time you write a program, it's technically an intelligent program, right? But the idea here is how can we design algorithms so that the computer can adapt and achieve a particular goal, right, given a set of inputs of data, right? So instead of manually creating intelligence, right, like we've been doing for a long time, can the computer actually figure out and make those decisions, right? So it's basically, the idea is, can you automatically model or learn from data without explicitly programming it, right? So that's what I think of the definition of machine learning. So there's a number of different techniques. So here are the three main categories that I like to think about machine learning. So first, supervised learning, okay? So supervised learning is a type of learning in which the data is labeled, okay? So what do I mean by the data is labeled? That means that the data set coming in from the application has a particular tag or meta information attached to it, right? So for example, you might want to attach a label to a certain button on an application, like a login button, or maybe a submit button, right? So the data is labeled. The second category is unsupervised learning, okay? So this case, there is no label, right? We don't have any understanding necessarily of the structure of that data, right? So the idea for the supervised learning is to structure it, right, in a way that we can understand. Unsupervised learning, we don't know the distribution, right? We don't know the distribution, so we have to figure out how can we learn what those distributions are. And then finally, reinforcement learning. Basically, the idea is to build a model that maximizes some reward or some score, okay? This is very popular in, I don't know if you guys are familiar with the game Go, and Google built a machine learning model using reinforcement learning to play the game Go. And actually, they trained millions of examples, and it actually performs better than a human, right? But it's a type of reinforcement learning. Right, so in that type of case, the objective is to maximize your score, right? You want to maximize the score. So what decisions can you make to maximize that score? So there are two types that you can break supervised learning into. There's continuous data and discrete data, okay? So if you have continuous data, right, the data set is continuous, that we like to call regression. So most commonly, linear regression, right? So many of you have probably done this. You have maybe a scatter plot, and you try and find a line that goes through it, the line of best fit. So that's called a regression. Then you can also have a case where there's discrete data, okay? And that we like to call classification, right? So you try and classify the data into different sets, okay? So then for unsupervised learning, we don't necessarily know the distribution. We don't know, is it continuous, is it discrete? We don't know. And this type of approach is typically clustering or association. So I'll talk about this a little bit, but things like k-means clustering, okay? It's a type of unsupervised learning. And then finally, for reinforcement learning, there's two sets. There's discrete data, or in an unknown case, we call that control, right? So this is basically you controlling something, maybe a robot, maybe software, right? In the discrete case, it's called classification again. So this is sort of an overview of how I would like to break machine learning into these main categories. So the challenge is, can we apply machine learning, those techniques, to big data sets? Okay? And so it's not always obvious, but yes, we can, but there's some challenges, okay? The first challenge is, how accurate are these models going to be? Right? How accurate will the models be? So there's a trade-off between what's called bias and variance of the model, okay? There's also what's called the curse of dimensionality. So what that means is, if you have a large data set that's high dimensional, right, it's very difficult to find good, accurate models, right? So the higher dimensional the data is, the more difficult it is to find models that can fit, okay? So So there's some tricks you can play to reduce dimensionality, and that's a whole topic of machine learning, is actually taking high dimensional spaces and mapping them into smaller dimensions. And then there's also the scalability performance issue, right? So you can imagine you have billions of data points, right? How long does it take to train models, right? You know, how scalable are they? Can we scale them out to millions of users, for example? So those are the main challenges that, you know, we try and solve in industry. Let's talk a little bit more about this one. So this is the bias versus variance. And many of you may have already seen something like this before, but I just want to go over it because it's very important, right? So if you have a model that's biased, what that means is there's error introduced from some assumptions in the model, okay? So what that means is your machine learning model is underfit, okay? And if it's underfit, it has a high relative error, right? The alternative is you could have a model with high variance, okay? So if a model has a lot of variance, that means it's overfit. So if you think about it, if the model is overfit, any small error in the input has, it's sensitive, right? It's very sensitive to any error introduced, right? So it's overfit. And so you can see that's on the other extreme. So in the ideal scenario, you have to balance bias and variance to find an optimal point, right? So on that curve, you can see somewhere in the middle between bias and variance of the model we try and achieve. Okay, does that make sense to everyone? Okay, good. Let's go into some examples of things we do. So one example, and this is a type of classification, we use what are called convolutional neural networks. Okay, so a convolutional neural network basically is a sequence of steps. First step, obviously, is typically we use these for classifying images. Okay, so if you think about from a testing point of view, we have an application, we can take a screenshot of the application. We can then, through using a convolutional neural net, we can classify different pieces of the application, right? We can classify buttons, we can classify text, we can classify images, right? So how it works is basically you have a number of steps, right? So there's a convolutional layer, followed by a pooling layer, then another convolutional layer, and there's a sequence of these. And then at the end, there's a fully connected layer, and then we use softmax, and then that will classify it into different types of classifications. Okay, and so this typically is very good if you want to classify general things. Like there are many examples you can find on the internet how people have used these to classify animals, different types of image data. Right, but for us, what we do is we use this to classify web applications, right, and mobile applications. So that's one example. Another example of a model we use what are called hidden Markov models, okay? So in a hidden Markov model, right, each state has a probability distribution, and the idea is, can we learn the hidden states, right? So for example here, we have x1, x2, x3. These are the hidden states, okay? And we're trying to predict a sequence of data. And the idea is that there's a probability distribution attached to each of these states, and we try and learn what that is. Okay, so this is another good example. People use this, for example, in handwriting recognition. It's a very popular example of this. We do some of this as well for classifying image data, but also sequence data, right? You can use hidden Markov models. Another one, Markov decision process. This is a type of reinforcement learning, okay? So the idea here is can we choose a policy to maximize a reward? And that's what I'm talking about in this case, right? So you're taking the sum of these rewards. So each step, each state, right, you try and figure out what is the reward, right, of actually taking an action, right, and changing state of that application. So if you think about it, let's say you have a mobile application. There's many different options you can choose, right? There might be 10 buttons, 100 buttons on the page, right? So how do you figure out, in order to find bugs or find issues in software, how do you figure out how to navigate that application, right? And so we can use things like Markov decision process to do that, to help us make decisions in how to actually navigate through software. Okay, this is another example. This is a type of unsupervised learning called k-means clustering, okay? The idea here is partition the data into multiple sets. So you can see over there you have the red, the blue, and the green sets, right? And the idea here is you're trying to minimize the error, right, between a mean. Okay, so this typically assumes a Gaussian type distribution. And what you want to do is you want to minimize the error. So we can use this, for example, for clustering data in an application, for example, visually, right? So you might have many, many buttons that might be associated to one another, right? And we would want to cluster that. Maybe you have a menu drop-down, and you want to cluster that data. So we can use things like k-means clustering to do that. You also might apply this to behavioral data. So another source of data we collect, obviously, is we collect traffic of people that visit these websites, and we can sort of cluster them into different types of user categories, right? Or user actions, right? We also call them user journeys. Basically, so you can have, for example, maybe there's a segment of people that visit an application and they log in to check their account, right? So that could be one cluster of users, right? There might be other users that visit the application and they go and they want to read the blog, right? So we can actually take this sequence of actions that they take on a website and cluster them into similar segments and do analysis on that. For example, we can identify anomalies in that data. Another type of clustering is called expectation maximization, okay? In this case, we want to maximize the likelihood function of a model. This is another type of clustering you can do. The advantage of this one is you don't necessarily assume any type of Gaussian distribution, right? So there's an expectation step and a maximization step. And you keep iterating back and forth, right? You produce an expectation function, and then you try and maximize it to basically find different clusters in data. And this typically performs a little bit better. But it depends on what your data looks like, right? And this is another type of unsupervised learning. Here's another one, reoccurrent neural networks. So this is good for sequential data. That's something we use for natural language processing, okay? So what you have is you have a sequence of neurons set up. So for example, you could feed in a sentence, right, into these neurons. And through the process of what's called back propagation, and I'll explain that in the next slide, you can actually learn what that sentence means, right? And you can figure out the different components, right? The different parts of speech, that type of thing. And so this is something we do when we process natural language in our platform, as we use reoccurrent neural networks. So and here's an example of what back propagation is. So what we do is, in order to back propagate, what we do is we measure the gradient between these different neuron layers, okay? But one of the big problems in doing this is that gradient will vanish over time, right? And potentially exponentially, or it could explode, either case, right? So as you back propagate, that gradient becomes smaller and smaller and smaller, so those first layers become almost meaningless because the gradient may be zero at that point, right? So this is a major problem, right, in trying to find good models that fit data. But there's some solutions, and one solution to this problem is what's called LSTM, long short-term memory, okay? So and this is designed to improve that problem of vanishing gradients. And how does it work? Well, it works because there's a memory state in the neuron that can actually share information across layers as it goes through, right? So you can actually share information that's important, right? Because what the backpropagation is trying to do is trying to figure out the weights of those neurons to figure out what is important in classifying your data, right? And so in an LSTM type model, you have these states that can actually exchange that information across the layers, so it can reduce the problem of vanishing gradients. So this typically performs very, very well. And it's good for sequential data, right? So if you have time series data, it's very good. I think some people have probably used this to predict like the stock market. I don't know how well it did, but it's something you can do, right? We use it for obviously measuring behavioral statistics, visitors on websites, trying to identify different anomalies in the data and to predict what's actually happening on your website. Okay, so those are some examples of techniques. Has everyone sort of heard of these before or understands what they mean? Okay, good. So then I want to go into one other part of the discussion is called boosting. So let's say we have a model that we've trained, and maybe it's not so good, right? And maybe it's only 60% accurate. Is that something that we can use, right? So by itself, no. But we can use a technique called boosting to actually turn weak learners. A weak learner is basically a learner that is not very accurate. Maybe it's just a little better than random, right? Better than 50% accuracy, and actually build a stronger learner out of them. So this is an idea of a hybrid type model, right? Combining models together in a boosted fashion, okay? And why is this useful? Well, this is one way we can improve the modeling in high dimensional spaces, right? You can imagine you can build smaller models that look at certain dimensions, and then through boosting, combine them together to get a model of the whole data set, okay? Some examples called eta boost, gradient boost, and legit boost. So those are some examples of boosting techniques. So what is a weak learner? Like I said before, a weak learner is a model that basically performs slightly better than random guessing, right? So if you were to just randomly guess, what is the classification of this data, right? A weak learner performs just a little bit better, okay? So the benefits, what are the benefits? So it has low variance, right? The data is not overfit, right? However, it has high bias, right? It's very biased. It's underfit for many complex situations. So the idea of boosting is we can actually improve this type of model. So let's go through an example of this. So let's say we want to classify these dots into yellow and purple dots, okay? So one thing we could do, let's say we just guess a function or a model to classify them, say F1, right? Draw right through the middle. Okay, now is this a good classification? Yes? It's okay, right? So there has some problems, right? So there's some incorrect classifications in that data, in that model. So what can we do? But it's better than just randomly guessing the classification, right? It's a little bit better than that. So what can we do? We can try another model, okay? Maybe this one's a little bit better, okay? So it doesn't misclassify any of the purple, right? But it misclassifies the yellow. Maybe we try another example, F3, right? And so what we're doing is we're basically building a sequence of okay models, right? And then combining them into a much better model, right? Okay? So the purpose of boosting is you can take these maybe binary classifications and combine them into a stronger model that fits a nonlinear situation like this, right? So you can see if we just continue to pick different types of classifications, we can eventually end up with a much better hybrid version. And so it's very simple. So you basically sum these different models together, and then there's an error introduced, right? So there's an error function introduced. So you don't want to use too many models, right? Because then you'll obviously increase the error as well. But you want to use just the right amount, and you can test, right, what that error is. And at some point, as you iterate, you can stop at what is acceptable. Okay. So, but you can also end up with situations of overfitting. So, right, so is this model overfit? Right, maybe this is noise, right? Right. So there's a trade-off, right? How many models do you use before you overfit the data again, right? So there are some tricks. So is the error bounded? Yes. So this is the equation, right? So it's the number of boosting rounds. So it's the square root of this, square root of TD over M. Okay, so it's the number of boosting rounds, the complexity or dimension of the weak learner, and then the number of training examples. Okay, so that's how you can check to see how good your error is. Does that make sense to everyone? Okay, good. So now I want to go into some more cases that we've done. So another case, this is a real example, and this is something that Julio has helped me with, of using a Markov chain. So what we did was we collected data on what users do, and we built a Markov chain right here. And so as you can see, we found some correlations in that data. So for example, 100% of the time, a user will hover over a button before they click on it. Makes sense, right? 90% of the time, you init a page before you verify any information on that page. 75% of the time, you have an input before click. So what does that mean? That means that's typing in a form, right? If you have a form field, like maybe you want to submit some information, click submit. So you input some data and you click submit. So these are some interesting correlations we found in actually analyzing real user data on real applications. And so what we've been able to do is build a Markov model. And this is basically a visualization of the matrix. Okay. So you have a page in it. You verify. So you verify meaning you're trying to verify that the page loaded. Okay. And then you have clicks, inputs, hovers, that type of thing. So these are the type of data that we work with and try and model, right, on a user's application. And then what we can do with this type of models, we can analyze if there's some type of an error. So for example, let's say that you have a website and you expect the users to log in. Well, if that login is broken, that will adjust the probabilities of this model. Right? So if you continuously model this over time and a functionality on the website breaks, you can quickly identify what happened, right, using this type of model. We also did some visual element classification. So these are some examples of bounding boxes of elements. There should be a drop down here. And what we're able to do is actually cluster them and identify different sections of a page, right? So, for example, you have maybe down here is like the content of the website, and maybe you have a drop down, right? Maybe you have some navigation items. So that's kind of an example of some clustering and data, visual data classification that we've done. So it's very cool. So one of the main problems visually is websites change dimension. Everyone's computer has a different resolution, right? So I might have 1,000 pixels wide. You might have 2,000 pixels wide, right? So websites scale, obviously, with the dimension of the page. So in order to test pages of different resolutions, we want to be able to have good classification of the data. Okay. So that's some examples of some of the machine learning techniques we use. Okay. I want to say a special thanks to Julio and Omar for helping me with some of the analysis in this presentation. And with that, any questions you have on what I presented? No questions? Yes? Developing software?
Theoretically, it's just translating. You can use like
Yeah.
natural language to
Yep.
determine the intent and translate it to code. How far do you think?
So there's definitely a lot of efforts right now to do this sort of thing in terms of when it would happen. I mean, so right now you can do this on simple applications. The problem is a lot of the stuff that we do, especially in the enterprise world, is very complex. Every business has a different logic, right? And it's not really something you can just learn, right? Because everyone has a custom scenario. For general things, maybe you want to build a game, right? You can do it, right? You can already do it. If you want to build maybe like the game Pong or something, you can automatically do that probably, right? But a lot of these enterprise level things, I don't think it's anytime soon, right? So I think for developers, you're probably safe. Your jobs are safe for now, right? Right? But for simple applications, you can learn them. I mean, there's many examples in which people have used machine learning to, for example, automatically write music, right? Write music or write papers, right? You know, I think there was an example in which someone used AI to write an academic publication, right? Obviously, it takes a lot of examples, right, to do so, but it can be done. Now, it didn't really mean anything, right? Right? The paper that they actually generated wasn't really meaningful, but it looked exactly like an academic paper, right? But no, I don't think we're anytime soon to a general purpose AI that can do that, but for simple things, yeah, I think we can do that easily.
So maybe if big systems
Mm-hmm. Possibly, yeah. Mm-hmm. Yeah, for example, maybe you could easily develop a login system automatically, right? That could probably be done, right? Or maybe a blog. Well, I mean, a lot of people, I mean, there's a lot of like templates and stuff out there that exist for these types of things, right? Or libraries that you can use, right? So how do you sort of join them together? That's where it becomes more complicated. And then also the architecture involved, right? Because if you want to design an application to serve millions of customers, that's a little bit more tricky, right? And just maybe a simple app that only handles thousands of customers. Yeah, so one of the things, I used to work with Apple on iTunes, the iTunes platform, and help them develop iTunes. And there you have, you know, a system in which you have 1 billion users, right, using that system. And it's the architecture is very different, right, for that than maybe a simple website. Right? So that's something that machine learning, I think, would struggle with, right? Unless you had enough examples of that. But of course, you go to Apple and ask, oh, can we get all of your data? And they're not going to let you do that, right? To train, right? They won't let you. So, any other questions? Yes? Mm-hmm. Some guarantees? In terms of time or in terms of accuracy? Yeah. Mm-hmm, mm-hmm. Yeah. No, we do have some. We do have some. Yeah, we do have some rules that we try and enforce. So, for example, we try and build. So, when building actual tests, because there's a lot of computation, we actually try and produce those within a couple hours. Is sort of our time right now that we guarantee. Right, so we can produce tests within a couple hours, and the testing itself typically is done within 10 minutes after they're developed. Right? So it takes a lot of learning to figure out what tests to actually do, and then the execution is about 10 minutes. So that's sort of our guarantee. Right? If that makes sense. In terms of bugs, I mean, every application has different levels of bugs, so we can't guarantee, oh, we're going to find 100 bugs, right? Because maybe there's 0 bugs, right? Or maybe there's 1. We don't know. So we can't necessarily guarantee we'll find so many. Does that make sense? Yeah. Yeah?
Can boosting help when you have few data?
With a few data?
Yeah.
Yeah. So we have had examples in which we had a customer that only had 100 users on their site, right? 100 users. And we tracked some of the data and we're able to build some test cases. Now, the problem with that is you don't get good coverage. So you might have a very big application, but if you don't have a lot of people, you know, navigating it and clicking on different things, you're not going to know exactly what is important, right, until you have a larger user set. But you still can find correlations. You can still find key test areas, right? So we would try and identify not just like every possible test, right? There could be infinite combinations of buttons, right? But what tests have high business value? So for example, like I keep bringing up the login. If users can't log in, that's critical to the application, right? That's a critical, you know, thing to test, right? So we can identify those core areas with a small subset of users. But in order to get full coverage, you do need larger data sets, if that makes sense. Yeah. Yeah. Mm-hmm. Yes.
You get redirected to, I don't know, the landing page
Mm-hmm.
instead of my draw.
Yes. Yeah, that's something we can test. Mm-hmm. Yep. Mm-hmm. Yeah, exactly. Exactly. So yeah, so we collect a lot of examples and then we can identify, you know, oh, we went to a page and we shouldn't have, right? Because we can visually identify that page, right? The structure of it. Yeah. Mm-hmm. Yeah, so it's a good question. So a lot of customers, especially in the Silicon Valley, a lot of big IT companies typically have a release schedule of about 2 or 3 weeks. Okay, everyone's a little bit different, but 2 or 3 weeks is typically the time frame that we take to develop those tests. That's I would say about an average time. And that's about the time it takes from you to go from release 1 to release 2 to release 3. Right? So every 2 or 3 weeks there'll be a new version, right? And so this works well because it almost never happens in which you completely rewrite your software. Every time a company releases a new version, 95%, I would say, is the same code. They only tweak a little few things here and there, right? Add a few features, type of thing. But 95% of it is the same, right? And that's why we're able to develop those correlations over time, right? And then find in those small issues that arise, right? Because most of that code is the same every time. But in terms of time frame, like usually a couple weeks worth of data. But depending on the customer, it could be gigabytes, terabytes of data even. Right? So I don't know how much data we have now, but it's hundreds of terabytes, I think. Right? Quite a bit. Yeah. Any other questions? No? Oh, one more. Yeah.
What's the largest physical code
Largest piece of code? Yeah, so one of the largest piece of code, so right now we're testing Cisco, actually, Cisco routers, and which power about 55% of the internet. Right? So you probably have Cisco routers here even. And that's a code base in tens of millions of lines of code. Right? And thousands of developers. Right? And they've been developing it for 15 years, 20 years, right? So yeah, big, big, big pieces of code. Yeah. Any other questions? No? Okay. That's it for me.
Pues le agradecemos muchísimo a Jon Seaton